Welcome to Answer Everywhere. This is a live show where every episode we dig into a source code repository completely unencumbered by any sort of preparation process and do some code archaeology. Try to see what makes it tick, try to figure out if there are skeletons, burial remains, the usual archaeology stuff. So today we are looking at JanusGraph. This is a graph database. We looked at another graph database called Neo4j on Wednesday. And if you take a look at the opening of the Neo4j episode, I talk a little bit about the trade-offs between a graph database, in this case, JanusGraph and Neo4j are called property graph databases. Between these property graph databases and using a traditional relational database like MariaDB or MySQL or Postgres for storing your graph data, doing your graph queries. The TLDR is that there are cases in which relational databases seem to work just fine. I don't know. I didn't read the paper. There are a couple of papers that I looked at. I didn't read them close enough to know when exactly they are. But it seems to be the case that you don't necessarily need a special graph database if you want to do graph stuff. But if you do have a big enough data set and a specialized enough need for graph stuff, then you will probably want something more graphy. And so that's what we're going to look at JanusGraph for. And I see some stuff in the chat. Hi, Karin. Yeah, it's been a long time. It's good to see you again. How have you been? I've been seeing more and more people popping in who haven't been around for a while. Did I change my hairstyle? I don't think so, not intentionally. I've had, kind of just depends on the day. I think mainly what my hair has decided to do and what the weather is. All right, so maybe one more thing before I will start is that JanusGraph started as a fork of Titan. And I guess maybe the name is some sort of reference to its lineage because Titans are like the pre-gods of ancient Greece, right? Before I guess they got the Proto-Indo-European gods like Zeus. Or maybe just part of it, the same tradition, just, a generation older. And then Janus is the god of what? Doorways and double faces and transitions. A Roman god. Let's see. Here we go. Beginnings, gates, transitions, time, duality, doorways, passages, frames, and ending. Frames and ending. I don't know if that's like window frames. So here's Janus. Janus has two faces, looking, I guess, fore and aft, or left and right. He has no flamen. Was there a Greek version of Janus? Had no known equivalent to Janus. There's considerate overlap with, I don't know how to pronounce this, Coulsons, the Etruscan pantheon. Okay, so maybe he comes from the Etruscan people. I don't know. At any rate, I don't know what we're supposed to be looking two-faced at with JanusGraph, but I do know that when I look at the code, it looks so much better and so much cleaner than Neo4j. If you watch the Neo4j video, I was often struggling to figure out where implementation stuff was. Things weren't always named the way that I expected to. Sometimes the name of like a function or a variable would be a full English sentence. I poked around it just a little bit on the JanusGraph code base, and it seems to be a much cleaner layout. And in particular, just in this root directory, we see it's 98.8% Java, so we're not going to run into the Scala issue that I ran into last time. So here we see a couple of things that seem like they're really clear. One is we get backends like JanusGraph Bigtable. Bigtable is a backend that you can use with JanusGraph. We get examples, which will show you things like configuration, I think. gRPC, I'm sure they use gRPC internally. I'm not sure. Maybe this is just a gRPC interface for if you want to call graph from your gRPC stack. We also have Hadoop. Hadoop is another possible backend. Apache HBase is a backend, I guess, in memory is a backend and some sort of Lucene support. I don't know if Lucene is a backend per se. I don't think it is. I think it's a search library rather than a thing you can run. And I don't think we get a README. Maybe here, no? I guess Lucene for indexing. Just like we saw on Neo4j, they also used Lucene for indexing. Hi, Tat. How am I doing? I'm doing great. How are you guys doing? All right. So what I'm going to do, though, is I'm going to jump into, I'd like to see where the guts are. And I remember that being pretty clear as of a moment ago. Hey, JanusGraph core looks very promising. Okay, so here's core. We'll go into source, main, JanusGraph. And already we get things that was a little bit opaque in Neo4j, at least to me. So maybe Neo4j just has its own style, and this style is just closer to the one I'm used to. I don't know. But we have disk storage, which tells me that it's for disk storage. We have GraphDB, which I'm not so sure what it is. Maybe that's just the like the entry point to the handle that has the connection. I guess we'll look at it, and then I'm going to guess core is important. Let's maybe take a quick look at Graph of the Gods Factory. Sure. We're going to do gods. Example graph factory that creates a JanusGraph based on Roman mythology, used in the documentation and examples. Okay, so let's just see how, presumably this graph is stored on disk in some format. And so I guess what they're going to do is maybe import the data and set some things up so that you can search for it. So let's see, I guess, how this is used. Sometimes with a complicated enough piece of code, a nicely written example can tell you a lot about how it's set up. All right, so we've got this create function that's going to return the JanusGraph, and you're going to pass in the directory where I guess it will find the thingy. And Berkeley JE, I'm not familiar with. I'm familiar with Berkeley DB, and this is similar. It starts with Berkeley and has 2 letters at the end. But let's see if we can find what Berkeley JE is. A distributed graph database. But this is JanusGraph. Is Berkeley JE part of JanusGraph? Jet drive. JE store manager. Do we get any sort of README? My guess is it's a Berkeley DB type thing, possibly created by JanusGraph that's specialized for storing graph data. Let's ask ChatGPT. Berkeley JE in the context of JanusGraph. So there's the Berkeley Database Java Edition. So maybe Berkeley JE is just Berkeley Database Java Edition. Okay. So it's the Berkeley database, which I forget how it works. I think it's a KeyValueStore, right? It's specially designed for Java applications, an efficient and reliable way to store and manage structured data within your Java applications. Okay. So tell me about Berkeley DB storage format. Yes. Bye, Karen. Great. Well, thanks for stopping by. Thanks for saying hi. All right. So for Berkeley DB, embedded database library, I guess B-trees. And they've got pages and nodes. Each page can contain multiple data items. Yeah. Everything's stored in a B-tree. We get key compression and caching. So we've got B-trees. Before, on the Neo4j video, I was being told by various AI assistants that data was stored in linked list format, which I think should be different from a B-tree, although maybe there's some way of doing it. So I'm not sure if Berkeley DB is the standard way to store graph stuff. Maybe not, but we'll look in the storage directory. At any rate, we're going to look, I guess, for we're going to set the storage backend, set the directory to this thing, and then we're going to open from the config object. And then we're going to call Graph of the Gods Factory load. And maybe this stuff isn't stored on disk. So where's load? Load. So open management, I guess that opens some management object. We've got some locks. Set consistency with a consistency modifier lock. I want to know what set consistency does. Yeah, I'm going to have to jump to Emacs because I think GitHub is not giving me what I need and what I crave. Okay, so defining a property. Whoa. You stop it. I'm going to jump to Emacs now because GitHub has started making it so that every time I hover or click on something, it like pops the thing up. And they've also made it explicitly so that when you try to search, it tells you need to log in. And that hurts my feelings. All right. Let's try this. Okay. So here's things in Emacs. And I was looking at load. Okay, here's the actual graph. Let me try making this smaller while also, yeah. All right. So here's the actual graph. We just have a few. We have Titan, name, Saturn, age. 10,000? So I'm guessing Titan means the type is a Titan. Oh, up here we have vertex labels. Things can be a Titan, a location, a god, a demigod, a human, or a monster. Okay, so Pluto is a god. Saturn is a Titan. He's the one who ate his children, if I remember correctly, and is identified or syncretized with Kronos in the Greek tradition. The sky is a location. The sea, so the vertex sky, the sky is a location whose name is sky, is the English string sky. Jupiter is a god who has the name Jupiter, and who's 5,000 years old. He's half as old as Saturn, I guess trying to reflect the tradition that the Titans are older. We have a bunch of other things. Okay, so these are the vertices, and then we have edges. And the edges encode properties like Jupiter is the father of Saturn. Jupiter lives in the sky. And the reason, I guess, he lives in the sky is he loves fresh breezes. I don't know if that's the reason. All right. And so somehow we had a transaction object, but the transaction isn't being passed into any of this stuff here. So somehow, so we call this management commit stuff before we do new stuff. So we create a transaction object. Oh, okay, yeah, we are calling transaction add vertex. Okay. And then here we're calling Jupiter AddEdge. And I guess the thing that makes this as part of the transaction is that Jupiter itself was returned from the transaction object. And then so when we commit the transaction, it's like serializing all the stuff and chasing all the pointers. Okay. All right. And so here's main. Main is just going to open the graph and load it and then close it. But is it going to do any sort of queries? I don't know. So I'll read this and returns this method, blah, blah, blah. Maybe in order to do a query, you have to modify it. Okay, so that's example. That's actually pretty illuminating. It tells me how JanusGraph thinks about vertices and edges, or at least how you code them up. I want to look in disk storage. So my understanding of JanusGraph is that you have to be pretty embedded, I guess, in the Apache distributed systems ecosystem. Like if you, or maybe the Google one. So you can use Bigtable, or you can use like Apache HBase or Apache Cassandra. There's some stuff about the Cassandra query language I think I saw. And I poked around in HBase and it said things like, if you want to use HBase, then you have to like upload this thing to Apache Zookeeper and you have to start some Apache Solr stuff. So it seems like if you're going to be doing like a scaled up JanusGraph in like an Apache HBase sort of environment, then you are like in Apache world. You are maintaining and running a lot of Apache related services. I'm not sure what life is like if you are using BigQuery, but then obviously you're somehow bought into the BigQuery Google Cloud world. But there are like I guess the Berkeley DB is a disk storage strategy that you can use without all the distributed system mumbo jumbo. And so with that in mind, given the fact that there are different backends, we should expect those backends to have some commonality, but also some differences. So like the way that you do column storage in BigQuery or Cassandra, those might be different. Those might be very similar, but it's probably a little bit different from how you like serialize stuff to B trees in Berkeley DB, assuming that's actually what Berkeley DB is doing. Okay, so let's look at backend. So this should at least give us the API for, look at all these import statements. Wow. This at least should give us the API for the backend. Let's see if there's a class. Here you go, public class backend. It's going to provide a lock and it's going to be auto-closable. And it will orchestrate and configure all backend systems, the primary backend storage, key column value store, and all external indexing providers. Okay, so we have some logger. We have a name for the edge store and a name for the index store and more stuff. What is this function? Register log managers. We've got these like capital letter functions. I don't know why they're capital letters. That's not how I was taught. I don't think I'm familiar with the convention in Java in which capital letters are used for functions. Let's see. Naming conventions. Internal words start with capital letters. Is this an Oracle thing? I'm not sure. Oh, start with capital letters. I'm not sure. Okay. I think that's just talking about camel case. All right. At any rate, we have this all cap stuff. And then we have things like a key column value store manager and some stuff for locking and more stores. I guess these are caches. KCVS, something key, something version something. I mean value something. Let's see what this thing is. Let's look KCVS. Computer science? Or maybe cache? Key cache value store, perhaps? I'm not sure. Or Kilkenny City Vocational School. That's definitely a possibility. All right. So we're just still setting stuff up. Here we've got a backend function which eats a configuration, I guess. Or is this the constructor? I think this might be the constructor if we're in the backend class. And we're going to do a bunch of setup. And I'm guessing just everything has its own, we've got managers and we're going to get indexes and all of that stuff will have different implementations depending on the backend. We have get locker. Not sure what a locker is. Maybe it's the thing that locks. We can initialize the backend. Get transaction logs. Build, store, index, scan job. Get scan, get user log, get storage manager. Okay. None of this is so surprising, but at least I have a kind of a sense of like what their backend API is. Let's look at entry. Entry is a primitive persistence unit used in the graph database storage backend. An entry consists of a column and value, both of which are general. The value may be null, but the column may not. Okay, so we're doing column storage, which I guess is traditionally used for things that are sparse. And that would make sense, I guess, for most graphs. And we can get columns, we can get the value, and we get cache. Okay. So does Berkeley DB do column storage? No? No results? I'm not sure. Okay, whatever, man. Okay, so a disk, an entry basically is what? It's got a column and a value. And the column is kind of like the key, if I understand correctly. And that's true whether it's a node or a relation. We have an entry list, which should be a list of entries, an ID authority, ID block. Is this like blacklisting? A block of IDs. Oh, maybe the ID is an identifier for the data. So let's look at this. So we have the number of IDs in the block. ID block must be completely thread safe. Okay, so how many IDs are in this block? And where the position must be smaller than the number of IDs in this block, similar to array access. Okay. And we can get the ID. Returns the ID of the given index. So we're like indexing into an array, essentially. Key column value is probably important. Permanent backend exception is not so important. Read buffer and scan buffer, etc., are not probably the most fundamental things. Is ID management interesting? Conflict avoidance, consistent key ID authority. Let's see if they have just mildly, might be interesting. Assuming that the backing store supports consistent key operations, ID blocks are allocated by first applying for an ID block, waiting for a specified period of time, and then checking that the application was first received for that particular block, and if so, the application is considered successful. So this might be, the implementation, I guess, might be backend specific. You're, I guess, requesting a block maybe from the backend where you can store data or something along those lines. Let's go key column value. KCV is key column value. So we can mutate a key column value. We've got some proxy object. We've got iterators for keys, a key range, and slices of keys. And I guess we can query stuff. And then we have key value folder and time to live. I guess maybe time to live in the key value storage. Let's look at base. What's fundamental here? I guess let's try looking at the proxy. So this proxy is going to wrap a JanusGraph disk storage key column value store as a proxy, as a basis for other wrappers. All right. I think we looked at that other thing before. What about mutation? So this basically, a mutation should be basically like a diff, right? So we've got a key, let's see. A mutation, you're going to pass it a list of entry additions and static buffer deletions. And there's this consolidate operation, which is going to call super on mutation. And you can check whether it's consolidated. What is mutation itself? So mutation has additions and deletions and an additions copy supplier. And we get that from where? Additions. Oh, it's the supplier type has these get methods, I guess. And what does that do? We set the additions and we set the deletions. I guess this is a constructor from a kind of supplier. Okay. And then what can we do with them? We can merge. Merges another mutation into this mutation. All right. So what should it do? It says ensure that all additions and deletions are added to the mutation. Does not remove duplicates if such exist. This needs to be ensured by the caller. Okay. So it's basically your job to make sure your mutations compose properly or whatever. There's a function to remove redundant deletions. And that's basically all. Can it like be applied? Is there like an apply? I don't know. Okay. That's mutation. Let's look at key column value store. Interface to store data that has a big table-like representation of its data. In other words, the data store is comprised of a set of rows, each of which is uniquely identified by a key. So you have a key for every row. Each row is composed of column value pairs. Okay? So each row has column value pairs, which is essentially means that a row is a key value store. For a given key, the subset of the column value, a subset of the column value pairs that fall within a column interval can be quickly retrieved. So I guess you get fast range access within a key, right? Within a row key. I'm assuming this means a row key. So the rows, I guess, kind of like form an index into a family of what I'm going to think of as like hash maps, key value tables, and once you index into a particular row, you get fast range access, I think is what this is saying. So we have methods for retrieving mutating data. This is a generic representation. In this generic representation, keys, columns, and values are represented as byte buffers. Okay, so this is the a generic representation that will be, I guess, adapted to the different backends. And we have things like get, slice, etc. All right, so cool. That at least gives me a sense of how they're thinking about disk access. And I think that's enough for me to feel like I have a sense of that. So let's take a look at what's in core. We get GraphEdge, JanusGraphEdge. JanusGraph element. Is an element the same as a vertex? No, because JanusGraph vertex is here. Let's look at vertex. That should be simplest. So it extends the functionality provided by Blueprint's vertex. What is Blueprint? I don't know. Can I go to this identifier? I'm not sure. I see Rux is saying, thanks a lot for teaching the core engineering beyond abstractions. Hey, no problem. That's what we're here for. That's what we're trying to understand. All right. So, okay. So this is a vertex. We can create a new edge. So a vertex can create an edge. You must give it what? Where it's going to go, the vertex, and a label for the edge. That makes sense. And I guess did we see this in the example? See if we can still pull up the example. I never know where to put this chat. Maybe I should have like a space above my VM. All right, I did just see Graph of the Gods. Here. What is it, AddEdge? Yeah. Okay, so we do see this AddEdge call. And as required, they pass a label and the vertex that you're adding an edge to. Cool. We can create a new property for this vertex and given key with specified value. Okay, so property, what does that mean? So is the edge like a row in this sense? Sorry, is the vertex a row, and then this goes in like the column store? Is that what's happening under the hood? I'm not sure. Creates and returns a new JanusGraph vertex property. Automatically creates the property key if it doesn't exist, and automatic creation of types is enabled. Otherwise, the method will throw an illegal argument exception. Let's see if return this dot property. I don't want that. Okay. empty args. Okay, so I guess what it's calling is this thing. And it has no implementation. All right. And we've got things like vertex labels, JanusGraph, vertex query. Okay, so that's relatively straightforward. Let's look at a relation. A relation should basically be a similar thing, except it has references to two, or an edge it's called. It should have references to two vertices, the start and the end. It should have a label, like the vertex does. We have an out vertex and an in vertex. Okay. Returns the vertex in the specified direction. The direction cannot be direction both. Why not? So we can pass it in direction in or direction out. Why can't it be direction both? Because it's two edges. Let me move this chat off for a second. Direction. Is this really the definition? All right, whatever. Let's find the definition of direction out. Here we go. No. I guess tags don't really work. These tags aren't really working for Java, so I'll have to come up with a new thing. Maybe I'll get a Java LSP thingamajig. All right, we can get the vertex at the opposite end of the edge. So you pass in a vertex, and it'll tell you what the what's on the other side, like the other side of the rainbow, and you can ask for its vertices. And really, that's all you can do with an edge. Cool. What's a connection? I'm going to assume this is the connection to the database. Connection contains schema constraints from outgoing vertex to incoming vertex through an edge. Schema constraints from outgoing vertex to incoming vertex. So I guess that allows you to say that, two things can't be connected in some way. So a connection, you're going to give it a JanusGraph edge, and it's going to get the labels, and it's going to look at the schema definition description and get its value, and something like getting a modifier for the edge label, and then setting connection edge to the thing you passed in. So this is modifying, or this is just setting internal properties like edge label. Okay. What does that do? Not sure. So I'm guessing that this is the thing that does whatever the schema stuff is. And I guess I'm not, so I don't think this is so fundamental that I need to dig into it, but I'll look up, see if there's any interesting documentation. That's for like WebSocket connections. How about schema? Schema and data modeling. Comprised of the edge labels, property keys, and vertex labels used herein. And it can be implicitly defined. You can print the schema. I guess you can do things like edge multiplicity. That might be one of the things in your schema. You can define property keys. All right, so single list set. There's different things you can do. I guess limiting the way that you construct your graph, and I assume that that's essentially what's going on here. And let's see what else. Let's see if we can find some of the optimization or the graph query logic. We have a query description. Let's look at the query description. This is, I guess, converted to a string. How many individual queries are combined into this query, meaning how many queries will be executed in one batch. So I guess this is for batched queries. You can get subqueries. Each subquery represents one OR clause. So for example, that is, it's a union of all the union of each subquery's result is the overall result. Okay, so you could say, give me all titans or gods. And titans would be one subquery and gods would be another. And a subquery knows whether it's fitted, that is, whether the return results must be filtered in memory. Or fitted, right? Okay. And whether this query respects the sort order of the parent query or requires sorting in memory. Okay. All right. That's cool. That's cool and all. What else? Oh, we are in core. What about... We have a base vertex query. Oh, JanusGraph query. Looks promising. Constructs a query against a mixed index to retrieve all elements. I don't know what a mixed index is. Maybe it's an index of both vertices and edges. So we're going to construct a query against a mixed index to retrieve all elements. Finding matching elements efficiently using this query mechanism requires that appropriate index structures have been defined for the keys. Okay, so you need to define index structures. I think these go in Lucene or something like Lucene. And once we have the indexes, we can query them. And that should actually be pretty straightforward because we're just using like a search engine utility to do it, namely Lucene, if I understand correctly. The returned element must have a property that the given key that matches the condition according to must have a property for the given key that matches the condition according to the specified relation. So, for example, whatever Q is Q query. Okay, so Q has key, predicate, condition. So I'm guessing if you call this, you're going to so the key is a property, and it needs to have the property and also satisfy the predicate with respect to the condition. Hi, QSM. Yeah, more Java. This Java is, in my opinion, much cleaner. All right. Has. We have a graph-centric query builder. This is probably interesting to look at. And we've got like a directive for OLAP. I don't know if that's because this is only for OLAP. Let's look up JanusGraph OLAP. Works with TinkerPop's Hadoop Gremlin package for general purpose OLAP to traverse over the graph and parallelize queries by leveraging Apache Spark. That's cool and all. In addition to online transactional processing, JanusGraph supports global graph analytics with its Apache Spark integration. I'm not even sure what Apache Spark is. It's an open source, unified analytics engine for large-scale data processing. Okay, but what is it? Is it a MapReduce framework? Limitations to MapReduce. It runs on a bunch of operating systems, but what is the actual type of thing? We've got Spark Core. So it does distributed task dispatching, scheduling, and basic I/O functionalities exposed through an application programming interface. So is it for like job control? It does SQL. I'll ask ChatGPT. So I'll say, what is Apache Spark from a technical / architectural perspective? And while we're at it, if I can spell architecture correctly, I think that I saw a diagram of the JanusGraph architecture. Is this it? So we've got OLAP and OLTP. OLTP should be transaction processing, and OLAP is what? Online something processing. How do I not remember this? Analytical processing. Okay, so for doing analytics. So OLTP, let's look at OLTP first. Applications are going to call into the management API, or maybe use the Gremlin, which is the query interface. There's an internal API layer. And then there's a database layer, which has things like transactions, data management, and optimizer. And we've seen, I think, transactions, maybe a little bit of data management. I don't think we've looked at the optimizer. And then there's a storage and index interface layer, which we've looked at a little bit. And then it's going to go to a backend, which might be Elasticsearch, Solr, or Lucene, or Berkeley DB, or HBase, or Cassandra. And then OLAP, it's going to go into Gremlin, whatever graph computer is. It seems to be different from the TinkerPop API. And it's going to use a big data platform like Spark, whatever graph is, and Hadoop via the OLAP interface. And it's going to use one of these backends on the left. In fact, only HBase or Cassandra. I guess Berkeley DB is not supported. And there's, I think, no mention of BigQuery. So maybe this chart predates it. All right. So ChatGPT is telling me that Apache Spark has some cluster management stuff, or it integrates with a cluster manager, like let's say Kubernetes or Apache Mesos. It's got a driver. It's got executors. It's got some worker nodes, I guess. Resilient distributed data set. These are, I guess, collections of objects that are distributed and partitioned across the cluster and can be processed in parallel. And then a scheduler, a DAG scheduler, and transformations and actions. Yeah, I think this is maybe like this next generation of MapReduce is what Spark is. I'll say, is this basically the next generation of MapReduce? And evaluate, yeah, okay, a success for MapReduce, great. Thanks, ChatGPT. All right, so we're back to the query stuff. This is querying the index. Let's see if we can find some optimization stuff. Is it in GraphDB? Maybe. Here's the OLAP directory. Let's look in query. Here we go. We have a query executor, a base query, a backend query holder, condition, graph, index, profile, vertex. Let's look at query processor. Wait, let's look at executor first. Executes a given query and its subqueries against the underlying data stored in transactions. So what should this do? This should execute the subqueries, ideally in parallel if it can, and merge the results, I guess. We can get new, which returns all newly created elements in a transactional context that match a given query. We can say whether it's deleted, and we can execute. And this is just an interface, right? Public interface. Can we find implementations? No. Maybe, I guess, find definitions in Java finds the implementations, right? Or maybe I can just search for I think this is telling me that the only for query executor is this one. So here's references to query executor. We get any extend stuff? What if we just search for extends query executor? All right, whatever. I don't need you. Okay, so let's look at query. So query has some stuff, whether it has a limit, and that's it. It's a thing that has a limit or might not have a limit. So what's a query processor? It will execute an element query against a query executor. It has a number of stacked iterators. All right, this is going to be interesting. So we've got a family of iterators, and these are going to do something. What are they going to do? I have no idea. At the highest level, the outer iterator ensures that the correct up to the given limit number of elements is returned. It also provides the implementation of remove by calling the elements remove method. That's the outer iterator. The outer iterator wraps the unfolded iterator, which is a combination of the individual result set of iterators of the subqueries of the given query. So I guess each subquery is going to have its own iterator. And those are combined together like Voltron into the unfolded iterator somehow. The unfolded iterator combines these iterators it should probably be, by checking whether, one, the result sets need additional filtering. Okay, so it might do some filtering. If so, a filter iterator is wrapped around it. And two, whether the final result needs to be sorted and in what order. So we saw this with is fitted and is sorted or something like that. I don't know if is fitted is a typo for is filtered, but maybe they have some concept of fitting that's like the opposite of filtered. I don't know. All right, so if the result set needs to be sorted and the individual subquery result sets aren't, then a pre-sorting iterator is wrapped around the iterator, which effectively iterates the result set out, sorts it, and then returns an iterator. So this is this stuff is kind of like reminiscent of coroutines. It sounds a little bit like. So there's going to be an iterator that has an iterator and some more iterators inside of it. And then there's some logic for when you pull stuff out of the iterators. And that's a little bit reminiscent, I think, of whatever the, maybe they're called generators in Python, where you like pass around an object and you have some rules for like, in theory that object could encode infinitely many things, and you just pull things out of it. It's kind of like the same way you would use laziness in a language like Haskell. So in this way, the individual sub-result sets are prepared and then merged together. The merge sort iterator, is this for doing merge sort, or is it a sort iterator that's merged? I don't know. Which conserves order if present. The semantics of the queries is or, meaning the result sets are combined. However, when has duplicate results is true, which assumes that the result set is sorted, and the merge sort iterator filters out immediate duplicates. Okay. Hi. Hi, ToomeyX. Welcome. All right, so what do we got? This query processor extends backend query and a bunch of other stuff. It's got some query executor. We're going to check that the preconditions on the query and executor are as required. I don't know what preconditions is. I'm kind of curious. I'll look it up later. And we've got a bunch of iterator stuff. And this should all just be implementations of the iterator logic, in fact, which is, I think, reasonably understandable if you're on board with this nested iterator stuff. Let's see if the merge sort iterator calls merge sort. Yep. Okay. But that doesn't tell us about optimization. We're still just working with, we've got a bunch of results from the things in the or clause from the back end, and we are just iterating through them. But here we go. Query profiler looks promising. And we've got some stuff about conditions. Some stuff about add nested, set annotation, start timer. Okay, so this is profiling in the sense of we're going to time the queries, I guess, and see how long they take empirically, which is different from optimizing them ahead of time the way that Postgres did. Let's see if we can find any optimization logic. Maybe it's in TinkerPop, transaction type optimize. Yeah, it is in TinkerPop. So we have a traversal utility, multi-query positions, query info, step, and strategy. Do we want step or strategy first? Strategy is going to be cooler. I don't know what step is. You might have a step folder. You might have a step or you might not. Let's look at JanusGraph step. Again, we've got the preconditions. Seems to be a Google thing. Okay. So a JanusGraph step extends a graph step. But what is a graph step? We're importing it from Gremlin. Okay, so this is a TinkerPop thing. We're extending it with our own stuff. And by the way, TinkerPop, it's the thing that that includes Gremlin. It's like I don't know if it's a standard or a library. Yeah, so Apache TinkerPop redirects to Gremlin. I'll ask ChatGPT. So it's a framework that defines a custom interface. So it defines the Gremlin language, the Gremlin abstraction, the traversal engine, some modifiers and filters, and graph algorithms. Okay, so Neo4j, we saw that there were graph algorithms directly in the Neo4j code base. It seems like maybe if JanusGraph is using TinkerPop, that perhaps TinkerPop has the graph algorithms there. And so JanusGraph might need to extend them, but probably doesn't need to implement them from scratch. Hello, Polyproxy. How goes? And folks, if you, I'm curious, if anyone has an interesting problem they've tried to, involving graph data they've worked with, I'd be curious to know. All right, so let's go back to Emacs. All right, so whatever a graph step is, in fact, let's look up what a TinkerPop graph step is. It should be related to traversals, like maybe one step in a traversal. What? This is do we not get a description? How about the documentation here? I'll ask Bard. In TinkerPop, what is a graph step? So we do get, did I close this? I thought maybe this is something I didn't have it, but we have something like coin step here. And it's going to call, I guess, graph vertex coin.05. Use the coin step filter, constant step, to specify constant value for a traverser. Okay, so maybe this is how much the graph traverser steps, perhaps. It's a step that returns the graph as its result. It is a subclass of the abstract step class and implements the graph computing interface. Okay, but what does it do? Doesn't matter. What do we see? We've got some query profiler stuff. Some stuff about queries. Maybe it's like a single step in the query, like a tick. We can build the global graph-centric query. Yeah, this seems to be doing query stuff. Not sure what it is. Maybe I'll come back to it. But, oh, what's a vertex step? Set multi-query. Register first, new loop. Oh, here we go. Here's like a full sentence. Register first new loop future vertex for prefetching. That's a long function name. Okay. And we can set metrics and stuff. And so maybe everything in the optimizer is really done in TinkerPop. Let's get out of the step directory. Let's go into strategy. So strategy, we have things like whether it has a step strategy, graph IO registration strategy, local query optimizer strategy, mixed index graph step strategy, multi-queryable step registration consumer. So let's look at the local one. Just for fun. It's going to extend abstract traversal strategy. Let's look at abstract traversal strategy. No, we can't because it's probably in TinkerPop, right? Cool. Well, maybe I should look at TinkerPop in the future. So we can apply a strategy. What else can we do? This is still apply. And okay, so what does apply do? It's going to check that the graph, I guess, is present. it's going to get the graph from the traversal. Basically, I guess, look inside the traversal object, and the traversal object must contain a reference, like a pointer to the graph or something. And we're going to get the transaction from the traversal as well. And then we're going to declare this property strategies mode thingy. And if the transaction is present, then we're going to get the configuration, get the vertex cache size, and get properties strategy and get property strategy mode. Otherwise, the transaction is not present, and we get that stuff, I guess, from JanusGraph in the graph config. And then we call apply JanusGraph vertex steps to the traversal. Then we call apply graph properties steps to the traversal, the cache size, given the cache size and the mode. And then we inspect local traversals. Okay, so what is apply graph vertex steps? So we're going to get the steps of assignable class and then do a for each loop over them. And for each original step, we're going to modify some stuff somehow. And how are we going to modify it? We're going to get the vertex step from the original step. Then we're going to replace it with what? Whatever vertex step is. Where did that come from? Here? No, I think this means we're going to replace vertex step in original step with traversal or something. I don't know. And then we're going to check if it's an edge return step, in which case, if it has a step folder with some sort of container in it, we're going to do something. You cannot fold in orders or ranges since they are not local, says this comment. Yeah, I have no idea what any of this is doing. So I think that to understand this, I need to understand TinkerPop, which is fair. And I guess if you were going to use JanusGraph, you would need to understand TinkerPop. So I might just stop there. That's about 57 minutes in. But before I go, let me think, is there anything I really want to see that I feel like I haven't seen any of? What is blueprints? A blueprint specific implementation for JanusGraph. I don't know what blueprints are. I'm guessing this might also be something TinkerPop related. So Tuna is saying, these Let's Read the Code series is awesome. The big code repos like Bash or JanusGraph are scary when you look at them. They are. And thank you for saying that they are awesome. They are awesome. Yeah, they are. I mean, all this stuff is scary. That's kind of the point. I'm glad. So they said that I make it more digestible, and I'm great. And they're grateful. Yeah, thanks. I really appreciate it. It's I would like to make this stuff not only more approachable, but also make people feel a little bit better about trying to understand some stuff, not understanding everything, but still walking away feeling pretty good that you haven't like slayed the dragon or anything, but you're better off than you were before. And I think that stuff like this kind of really compounds over time, like compounding interest. But if you're too scared to do it, then you don't ever get that goodness. Yeah, so I think I've seen what I want to see with JanusGraph, and I guess maybe unsurprisingly, they're using other stuff to handle a lot of the nitty gritty details that I was looking to see in things like Neo4j and Postgres. And that's smart, assuming TinkerPop is good and cool, and it does seem to be good and cool. And so if you want a TinkerPoppy Gremlin-based searchy thing, it seems like JanusGraph is a way to go. You have to find some way to store the data in a distributed way. But a benefit of having all the distributed stuff in it is that JanusGraph should, in theory, be able to horizontally scale very well. So you should be able to have lots and lots of nodes. And if you need more nodes, you should be able to add compute resources, like adding more VMs or adding new physical machines if you prefer to do things that way. Whereas something with Neo4j, at least my understanding is that like the community edition has some ability, let's say, to vertically scale. And then if you wanted horizontal scaling, you probably need to opt for the enterprise edition. So JanusGraph at least seems to be giving you that distributed nature more out of the box and not needing to pay a company to scale it out for you. So for what I'm building, that would be more appropriate than the Neo4j strategy would be. On the other hand, I'm not sure I have enough data to justify the complexity of running something like Apache Zookeeper or Hadoop or HBase or Cassandra or whatever all that stuff is. But I would like to see just a little bit about, I would like to know what a step is. It seems so fundamental. Is this where this is? Barrier step and step, aggregate step, add vertex step, graph traversal steps. Yeah, this is what I want. A graph traversal, SE. So a traversal is parameterized by S and E. Are these some things and edges? It's spawned from a graph traversal source. It can be spawned anonymously, that is empty, via, I don't know if that's a character that's not showing up in my CSS. Let's try turning this off for a second. No, it's just a literal double underscore, I guess. All right. A graph traversal is composed of an ordered list of steps. Okay, so it's thinking of a graph traversal as a list of steps. I guess you're going to first do this, then you're going to do that. Maybe first visit this vertex and then go here along that edge, that sort of thing. All the steps provided by graph traversal inherit from the more general forms diagrammed above. A list of steps and their descriptions are provided in the TinkerPop graph traversal Java doc. The following sections will demonstrate the graph traversal steps using the Gremlin console. And so we have things like general steps. There are 5 general steps, each having a traversal and a lambda representation, by which all other specific steps later extend. We can map, which maps the traverser to some object of type E for the next step to process. We can flat map the traverser to an iterator of E objects that are streamed. E is maybe, I don't know if E is edge or what. And then we can filter, map the traverser to either true or false, where else will not pass the traverser to the next step. Side effect, perform some operation. Okay, I'm getting at least a flavor of this. I don't know that I would have called these steps, but these are like, I guess, like composable. Like in the world of Gremlin, it seems like these are maybe like the sort of things that you would put Unix utilities you would put between pipes. There's some sort of piping, and the steps are kind of like the pipeable things maybe. And then I don't know anything about Gremlin, but I would guess that part of what's going on is that they've tried to organize this library of steps in such a way that it's easy to optimize, easy to parallelize, hopefully, that sort of thing. So I'm going to guess that that's what's going on. And maybe I will ask one of these engines, AI thingies, what it thinks about that theory. So Bard did give me an example of a graph step. Oh, it's telling me more. It's a step that returns a graph as its result. Okay, so graph step is a specific kind of step. It's one that returns a graph. And here's an example. You're going to open the thing. You're going to call graph step on G. And then you're going to add identifiers. And then when you call step.next, you get the graph back with your modifications. And I'll ask, what is a step? And I'll ask ChatGPT to draw an ASCII gremlin. What? No way. That's nothing, ChatGPT. We'll see if Bard can draw an ASCII gremlin. All right, so Bard is telling me about things like traversal steps, a unit of computation that can be used to traverse a graph. They're connected together to form a traversal. Okay, so they're easy to use. They're powerful. Solve a variety of problems. So traversals can apps be easily parallelized and optimized in Gremlin. Okay, so at least Bard thinks that they can be easily parallelized and optimized using parallel fork. I guess maybe you'll do this yourself. Allows you to parallelize traversal across multiple threads. Okay. Let's see. Will Gremlin automatically parallelize computations without your explicitly requesting it? So no, Gremlin won't do that. Okay, so I'll ask, will JanusGraph do that? Okay, so they say yes, JanusGraph will automatically parallelize computations. It's because it uses a distributed backend, has a number of features that can blah, blah. Here are some of the configuration options you can use to control parallelization in JanusGraph. Parallel backend ops. This configuration option controls whether or not JanusGraph will attempt to parallelize storage operations. Parallel backend executor service. Okay, and page size. And I'm guessing that it mainly does parallelizations by finding the appropriate backend, and then bringing them together. And I'm trying to think if there's anything like, so you would need, as the results come back in, and maybe those are the subqueries, and as the results come back in, you need to combine them, right? And so maybe that's part of what we saw with the iterator stuff. Is that things are going to different machines. They're coming back with different parts of the queries. And I'm not sure how you make sure that, there could be a case where a vertex on machine A connects to a vertex on machine B. In theory, that you should be able to get the whole two vertices in the relationship from the storage backend, because the storage should abstract that sort of nonsense from JanusGraph. So I'm not sure. I'm not sure really what's going on. Maybe that's interesting. I'm not going to cover it now. What I will do is ask Bard to draw an ASCII gremlin. This is a cow. Isn't this the apt cow? This is the apt cow, right? I'm not convinced this is a gremlin. All right. Well, that's all for me. I'll be back next week. I'm not sure exactly with what, but something cool. And I hope you have a good weekend. Thanks for watching.